Please help me welcome our speaker for the morning, Dr. Shelley Wright, Associate Professor of Physics at the University of California, San Diego, and Principal Investigator for the UC San Diego Optical and Infrared Laboratory. Professor Wright is an observational and experimental astrophysicist whose research focuses on understanding how galaxies and supermassive black holes form and evolve over cosmic times. Professor Wright earned her bachelor's degree in physics at the University of California, Santa Cruz in 2001, and her PhD in astrophysics at the University of California, Los Angeles in 2008. She specializes in the design and use of innovative astronomical instruments, particularly adaptive optic systems and integral field spectrographs. Professor Wright is also a SETI researcher and instrument developer. We'll take questions at the end of the presentation. For that reason, right now, I'll ask everyone to turn off their microphones. And with that, Professor Wright, welcome to the Greenway Talks online at Palomar Observatory. Thank you for taking time to speak with us today. And with that, please, the floor is yours.
Thank you so much. Wow, thank you. That was a really nice introduction. Let me start by sharing my screen. So today I'd like to talk about SETI, the Search for Extraterrestrial Intelligence, and the work our team is doing with a very large collaboration between Harvard, Berkeley SETI Research Center, Caltech. Some of the work I'll be showing you also involved Palomar Observatory, and then UC Observatory is at Lake Observatory. And well, Stephen gave me a very nice intro. I can't wear a lot of different hats. And so I run the Optical and Infrared Laboratory here at San Diego. And I spend a lot of my time working on instruments for Keck Observatory in Mauna Kea, Hawaii, in particular, those around adaptive optics. And then I serve as a project scientist for the First Light instrument for the 30-meter telescope and doing design work on that project. And then it was mentioned in Stephen's email, but I got involved with SETI very early on in my career at UC San Diego, working with Frank Drake and others at Berkeley. And I never left it, even though, 20 years ago, it was kind of taboo to work on SETI. And then I also like to study distant supermassive black holes and galaxies and how they evolve over cosmic time. So I work on a lot of projects. I have a large team of staff engineers in the lab. I have graduate students, postdocs, undergraduates that work on all of these fields. But today I want to talk about one of my favorite topics, which is, are we alone in the universe? So what we are looking for is something called technosignatures. And if you go back, I tried to find when that name was actually coined. It was coined by none other than Jill Tarter. So this comes from a quote from 2007. Jill says, if we can find technosignatures, evidence of some technology that modifies its environment in ways that are detectable. And that's really the essence of SETI, the Search for Extraterrestrial Intelligence. We're looking for intelligence, but we're looking for intelligence that is manipulating their environment and using technology for communication. So that's quite specific when we talk about life and intelligence in itself. And, her quote goes on and she really captures it well. She says, it's not possible to enumerate all the potential technosignatures of technology as we don't yet know it, right? So if there's another civilization using technology, we have no idea how they may be using it. But for our searches, we can define systematic search strategies for equivalents of our 21st century terrestrial technology that we use today. Yes, if we persist, humanity, our technology will get better, but we can only do as good as we can do today with our existing technology and the means for which we can do a search. And that is how I and others in SETI think about this. we try to think about how we would communicate across interstellar distances. And then we turn that problem around and we say, how would we detect such a signal? And how would we do that search? So this, to calculate all of those probabilities, I have to talk about in a SETI search, the Drake equation, probably the second most famous equation out there. Frank Drake proposed this in 1961 at a conference in West Virginia at the Green Bank Telescope. It was a small group of people. In fact, he recruited somebody named Carl Sagan to this meeting. And at that time, what they were trying to do is think about the probability of another civilization existing with us today that may be communicating. And so they put all of those probability factors there, for which Frank is doing a photo shoot, writing on the whiteboard. Now, I'm going to do a version of a Drake equation today. You can change this. I've seen this in multiple views in different textbooks. But today I'm going to calculate our view of, how many civilizations are existing with us right now in the Milky Way. So I'm going to do our math today. On the left side, I have the number of civilizations existing with us today versus the number of stars in our galaxy, the fraction of those stars that have habitable planets times the fraction of those with habitable planets that have life, then the fraction of those with life that has evolution and developed civilizations that uses technology. And then the big factor here that was flagged very early on in the early 60s is that you can multiply all of these things, but the things that matter the most is F of now. It's how long that civilization lives. So we have galaxies. We know that galaxies are made up of hundreds of billions of stars. This is my favorite galaxy of a nearby system. It's a spiral-like galaxy, and it's an SB Hubble type galaxy that's similar to our Milky Way if we took a face-on picture of it. It even has a companion galaxy at the bottom that's almost in similar mass of the Large Magellanic Cloud. And we have hundreds of billions of stars within these galaxies. So astronomers know quite well about galaxies, and galaxy makes up the numbers of stars within those systems. So if we look at that, I'm going to say our stars in our Milky Way, maybe we can say 200 to 400 billion, but I'm going to say 200 billion in this calculation. Now the fractional of habitable planets. Okay, this is the game changer, honestly, in SETI. When I started 20 years ago, people were still talking about rare earths and said, no, we can't do SETI. Earth may be rare. Earth is not rare, meaning Earth-sized planets are not rare. And in fact, the Kepler Space Telescope in this last decade has shown the statistics of what's called ETA-Earth, which is how common Earth-sized or terrestrial-sized planets are. And the answer is they are super, super common. That's amazing. That is a game changer, the fact that planets are common. If you have a star, you got planets. And not only planets, you got terrestrial-sized planets. So here's the statistics from this. This is the fraction of stars with at least one planet, right, versus the planet size. And Earth is sitting here with that fraction. And then you have things like super Earths. We don't have one of those in our solar system. And mini Neptunes, we're getting more creative, down to the most gaseous giant planets. So the statistics is basically 20%. So you count in fives, 1 out of 5 stars of a kind of solar-like stars, or down to even M-type star, will have a terrestrial-sized planet. So we can take that, and then you can say, what is the fraction of habitable planets? Well, habitability, we're not going to have a discussion on that. That's very important. We'll see lots of this about biosignatures in this next decade. But I'm going to be optimistic and say, well, 1 to 10% of those will maybe be habitable, maybe have water or something to develop life as we know it. Now, why? Well, when I teach about solar systems and astrobiology, what I'm constantly struck with is that I have to spend an entire semester just talking about possibilities of life in our own solar system. It's remarkable. I don't mean just life now. I mean life in the span of our solar system of 4.5 billion years, or 3.8 billion years for our terrestrial planet development. So we have Venus on the far left up here. Okay. All right, so Venus now is maybe not hospitable, but we even have interesting discoveries. If those of on the line like to think about that phosphine discovery and some of the latest missions that we want to go to NASA in terms of the upper atmosphere of Venus. But we know Venus early on, several billions of years ago, actually was more temperate. It likely had an ocean. We have geological evidence of that. And then we have our much smaller size planet, half the size of Earth, which is Mars, where we like to send all of our rovers to think about life in the past. We also know that Mars was also covered in oceans in the past. Now, that's just planets. And we also love to think about moons. So, we spend lectures and lectures talking about the amazing possibilities of life under the subsurface oceans of Europa, which is on the left. Here in the middle is Titan, a moon of Saturn, where it has completely unhospitable conditions to life as we know it with liquid water, but it has liquid ethane and methane. So we like to think about other things for life and biology in that type of system. And then, of course, other planets or other moons like Enceladus, okay, where we know there's other subsurface oceans. So you can then spend an entire semester talking about potential signs of maybe life here in our own solar system. That's just one solar system of 200 billion. Okay, so where does life exist on these solar system bodies? All right, so if life exists, now you may deviate from this. Everyone should do their own equation. Maybe you can do your equation with me now. So if life exists, I'm going to say something. If you have hospitable conditions for millions and billions of years, maybe it's optimistic, but you get 10, maybe it's 100%. Maybe this will just happen. Okay. Now the question now is intelligence. So we've had life on planet here on Earth for 3.8 billion years. It's taken a really long time to get ourselves where we can do a Zoom session like this. Okay, 3.8 billion years, it took a long time for us to evolve for this. And there's a really interesting thing to think about intelligence, and I love saying this word. It's the encephalization quotient. In biology, there's this really nice correlation where you see on the y-axis is brain mass in grams versus body mass in kilograms of the same species. And it's well correlated. And what you see is that humans on the encephalization quotient has the highest brain to body mass ratio than any other species on Earth. And the second one closest to us are dolphins. Now that's incredibly interesting evolutionary fact, a biological fact, right? But I also like to point this out because we are not the only intelligent life form on Earth. Okay, we don't just have, shower scum everywhere on planet Earth. We got dolphins, we got elephants, we've got dogs, we got very intelligent animals that do communication, but we only have one that uses technology. Now that really gets into kind of a world history discussion, which is then what are the characterizations and the definition of a civilization? And if we were in world history, we would get our 8 characteristics. And I always like to highlight this bottom one when I think about SETI, which is it's very interesting when we think about utilizations of chimpanzees or other intelligence. What's that dividing line between intelligence and, a civilization, so to speak, or podding of an animal, which is also characteristic, is this kind of bottom one. Usually it's the bottom 2. It's art and technology, right, that get in. So technology uses is important, which gets into our technosignature. So if we look at this calculation, you can think about the fraction of civilizations. Okay, I'm going to just throw out a number. I'm going to say you got billions of years, you get 1%. Again, maybe these are all overly optimistic. But as I already alluded to, the most important factor, if you just kind of move around your calculations there, will be F of now. So how long, if you do have a civilization, does it last? Okay, so our genus appeared 2 million years ago. Homo sapiens, right, really started about 200,000 years ago. And it took that time for the first civilizations, based on those definitions I told you, for us to appear about 3,000 to 7,000 years ago. Now, here's the kicker. Even if you have over that 10,000 years of our civilization development, only in the last 100 years do you have the technology to actually begin to do technology where you can send interstellar signals. So you have life on a planet for 3.8 billion years ago. You have our own species, essentially within the last 200,000 years. And it took that level of time to get to a point where we had the technological means of it. And then this is where we get into a lot of discussions. And it's very interesting to talk to freshmen and lecture on this and hear what their thoughts on it is how long would humanity's civilizations last? Is it something we self-destruct on, or is there actually a natural filter to this? Climate change, or I think Stephen was just talking about our Venus girl asteroid, right? So maybe there's something that just gets naturally imposed from the universe itself. Okay, so this is F of now. So F of now, I'm going to say, let's be crazy optimistic, maybe, that civilizations live for 10 million years. Okay. And if I talk to our freshmen just for this, nobody thinks this. But let's do this calculation I just set up for us. So if I do that, you get the number of civilizations in our Milky Way is about 1 in 100 million to 1 in a million. And that means that there are about 2,000 to 200,000 civilizations existing with us presently in the Milky Way. Now, if you're an anthropologist and you're thinking about the past, this is wonderful. That means that there's 2 to 200 million before us for us to study. Now, if you think that civilizations living for 10 million years is too optimistic, fine, let's change that. Let's say we only live for 10,000 years. Something happens here. Then that means that the number of civilizations is 1 in 100 billion to 1 in a billion. And if you take that calculations, if civilizations only last 10,000 years, then we only have 2 to 200 existing with us today. Now you can change those other factors again, and I invite everybody always to calculate their own version of the Drake equation. But it really is that fraction of time for which you coexist with another civilization that dominates the probability of detection. Okay, so this is a SETI talk, but I love to frame our probability factor in this of what we're really trying to answer here. Yes, we're trying to answer, are we alone? Okay, is there anybody coexisting with us? But if it also sets up this interesting thing where if you do make a detection, it gives you a very interesting constraint on the probability of these things, in particular, the lifetime of a civilization. All right. So if there was another extraterrestrial intelligence and a civilization existing with us today, what methods of communication do you think, or how would they be using technology to send us a message here on Earth? And we can look again at our 21st century levels of communication. So how do we communicate over long distances? Well, we can use mail. Okay, that's a dominant method of we doing communication, especially if we want to actually send material to someplace. And in essence, Earthlings here, we already did that. That's called Voyager and Pioneer. We've taken those satellites and kicked them out, and they're going to just go out there through our solar system. It's almost like a message in a bottle. We've also draped our planet in telephone lines in communication, and then of course evolved over that time to do long range communication using light, like radio wavelengths. And then everybody has a pretty advanced long range communicator that's using their cell phone. Now those last two involve electromagnetic radiation. And this really sets up the premise for astronomers in the field of SETI. So we use light, okay, and we use light because it's the fastest way to get any information. So it's your fastest carrier in the universe. But the challenge of this in our search is the fact that light, right, is infinite at infinite frequencies, and it's a function of energy. So our lowest energy light is at radio wavelengths. On the left here is our radio waves, okay? And that's good. If it's low energy, it's easier to generate, okay, and send a signal. And then you can go into higher energy wavelengths of light, or longer or shorter frequencies, microwaves, infrared, visible light, etc. And you have a lot of frequencies to search if you're trying to look for a signal. Now, Marconi, okay, one of, coined for being one of the inventors of the radio. Here's a picture in Life magazine in 1901. This is our beginning of our communication using radio signals. And since then, we've essentially been leaking out our signal, albeit at that point, at the turn of the 20th century, a quite weak leak signal. But over the last several decades, we leak out a pretty strong signal off planet Earth. And so any distance from us, basically within that last, 110 years, we have a volume of space that if anybody else was listening to us at radio wavelengths or TV broadcast wavelengths, would be able to detect us. Now, I always like to think about that volume of space for sending signals out. And, just so you think about this, in about 100 light year volume for sun-like stars, for G-type stars, okay, there's about 500 plus of those within 100 light years. And then that doesn't count the 10,000 plus other lower mass stars that are in that volume with us. Okay, so even in that small 100 light year volume, you're covering tens and tens of thousands of stellar systems. Now, this brings us into thinking about different types of SETI signals. Okay, and I'm going to go through 3 of these. We can think about them in different ways, but what I just described to you is basically called leakage. We're not intentionally sending a signal, but we are, right? So that's a leak. Anything that's within that volume and is searching and has a radio dish would be able to hear us here, okay? And we're just sending that out. The second one are what I like to call conversations, meaning not necessarily a conversation with us, okay? But let's just take this a little step up. Maybe they're in their own solar system and communicating, which we do, right? We communicate to our satellites to Mars, for instance. Or potentially, if you get a step level up and think about maybe they went to another star, if they're more advanced to us, there could be interstellar signals. And that could be interceiving conversations. And in SETI searches, we do think about this line of sight within their own solar system, the inclination of their solar systems to define some of our search strategies. Okay, so this is that example of the Mars network right now. We have rovers on Mars, but we have satellites in space that we actually send our signals and download those beautiful images that are coming from Percy and Perseverance right now back to Earth. Okay, the third one, which is kind of the dominant method we think about SETI, especially when we were thinking, early on about SETI, which is beacons. Okay, that means that they're intentionally sending a signal, meaning they say, okay, we want to announce to the other stellar systems that we're here, and we're going to, devise a way to do that where it would be easily detectable. And much of our searches in SETI involve this method, which is called beacons. Okay, so you have leakage, conversations, and beacons, and all of these ways we have to think about in terms of communication. Now, the first SETI search outside of our solar system, okay, was done by Frank Drake, and this was the famous experiment in 1960. Note that it's a year before, right, the conference in 61, where he invents the Drake equation, where he begins to use the Green Bank telescope here in West Virginia to look at potential signals, maybe leakage or actual purposeful beacons from 2 systems called Tau Ceti and Epsilon Eridani. Okay, and these were solar-like stars. So there was an assumption there that if you had to have life, you would need to be around a star similar to our sun. Since that point, much of SETI took off in the field of what's known as radio SETI. And radio is a fantastic way of doing long-range communication. And Jill Tarter did this work and used Arecibo to do what's called a targeted search. So she used Arecibo to look at 710 stars, all within a short volume of 150 light years, with that concept that they would know about us. And then this is the remarkable part of Jill's search with Arecibo, is that she searched over 700 million radio channels. I mean, next time you're in your car and you're like driving and you're like tuning in to find the station and you want to listen to, I mean, that should be mind-boggling, right? So 70 million radio channels to try to find the specific frequency of light. And it was the most sensitive radio search. I need to update my slide because until last year, there is now a more sensitive radio search. The other way to do this is another group at Berkeley used that Arecibo data. And of course, astronomers are using Arecibo all the time. And they said, why don't we just pick specific frequencies and then just look at large patches of the sky in kind of a commensal or piggyback mode. And this ended up in the development of what's called SETI at Home, which was a screensaver you could download in your late 90s, early 2000s that would process data. It's still existing today. But one of the most, remarkable things about SETI at Home was the idea about distributive computing, which took off at Berkeley and Space Science Labs because they realized that they could distributedly process, right, all of that search algorithms that they needed to do within these data sets. And that turns into many other discoveries later at Berkeley. Okay, so the answer to this, and the thing that I think when I meet people and talk about SETI that I try to get across the most, is that I think a lot of the public thinks that astronomers do SETI, like we're looking for signals, and that's just really not true. And the answer is that we haven't put that much resources in it either. We've barely searched. So this is a phase space at radio wavelengths that's showing right here the sensitivity, so how faint you can see something, versus the fraction of sky that you look at versus frequency. And I love this figure because it highlights the challenge, right, of the needle in the haystack. You want to look for faint things, you want to look at other large swaths of sky, but you don't know what frequency to search. And you can see at radio wavelengths here that they tried to do this by, doing the SETI at home method, where they looked at large fractions of the sky, but at particular frequencies, or Jill Tarter's Project Phoenix method in red here, which is going sensitive over many frequencies, but over only a few stars. And that's the trade-off here. Every SETI search has this issue. Do you try to trade off in fraction of sky or frequency search versus sensitivity? And these searches I'm just showing here are just at radio frequencies. So there was a lot of work also thinking about, excuse me, what other frequencies of light to look at. And interestingly, right before Frank Drake's Tau Ceti Epsilon Eridani search using Green Bank telescope, there was an amazing invention. So Charles Towns at Bell Laboratories invents the maser, or the laser. And Charles Towns, who was later a professor at Berkeley, was a remarkable man. I mean, very thoughtful. And he immediately knew kind of the industrial applications and how much the laser would revolutionize the world and our technology. But what's most striking is that he wrote a paper with Shorts and Towns wrote a paper in 1961 in Nature about how the laser would be an amazing way to communicate across interstellar and interplanetary distances. So he understood that a laser, because it was so bright and directional, we could direct it right at something, pack a lot of information in it, and recognize that it would be easily detected over many light years. Now, this didn't take off, even though this was a nice paper in 1961. Towns, by the way, writes a really nice paper in 1984 on this topic and takes it even further. But, thinking about today's technology, so today our highest power laser is 10 to the 15 watts. If we couple that with a 10-meter telescope, you can outshine our sun across the entire optical frequencies, everything across the entire visible spectrum by a factor of 3,000 and be visible over thousands of light years. So in 21st century technology, humans have the capability of sending basically a signal across the galaxy and being detectable by a small telescope. A telescope that's smaller, right, than the ones that are even at Palomar, basically. Okay, so that's remarkable. And that was even what Towns recognized, is that there was this ability to send large laser signals and be easily detected. I'm doing a cartoon rendition, by the way, of this, because this is exactly what, when we're thinking about conversations, what NASA's about to do next year, where they're going to start, instead of using radio technology to their satellites at Mars, they're going to do laser communication between satellites and Earth to Mars. And just since we're in the Greenway Talk series, there's a really nice experiment coming up that will be used on the Hale to try to do some of the detection of the Mars lasers this next year. Okay, so what about detection? I talk about transmission schemes. Now, it took till the late 90s to start thinking about how would we detect kind of laser signals, and not just laser signals, but bright optical transients, okay? But very fast transients. So one of the premises is about optical SETI early on was that you may want to pulse the laser to be easily detectable. So some of the first searches started. On the right picture here is Paul Horwitz at Harvard that did a dedicated telescope and had a graduate student there named Andrew Howard, who's now a professor at Caltech, work on a dedicated wide field optical SETI search. So they built this out, out in the woods. They needed to be on a larger site, but out in the woods past Harvard. And then the other development we did was where I got involved at Lick Observatory, where we developed an optical SETI detector with both Dan Hortheimer at Berkeley and then Frank Drake at Santa Cruz. And those were some of the first optical SETI experiments. And I want to talk about a few of those that then developed from there. So here is our galaxy. Okay, so this is the Milky Way at visible light. And basically for the Milky Way, you're always looking through the Frisbee disk, right? We live in the Frisbee disk. And between all of our 200 billion stars, we have interstellar gas and dust that's absorbing it. And so these black plotches here that you're seeing here is the interstellar dust absorbing optical or visible light. Now, what we'd really want to do, if you were going to search for lasers or other transients where you're looking at hundreds or thousands of light years away, you would want to move to longer wavelengths like the infrared. So here's a picture again of the Milky Way, but at infrared light, where you can easily see through the galactic plane. And I like to flip through this: visible light, infrared light, visible light, infrared light. And here's, by the way, the Large Magellanic and Small Magellanic Cloud here in the south. What's nice about thinking about this is that we knew early on if we were going to do laser signals, we would likely want to move to slightly longer than the visible light and go into infrared wavelengths. But that would involve kind of different types of detectors. And when I became a professor, I was very interested in working on, infrared detectors, which I was doing for my other work, and thinking about how to apply this to SETI searches. And this started a program which we called Near Infrared SETI. So what we did was took some of the concepts that we used early on in the optical SETI experiments, but applied it to near infrared detector technology. So about in 2014, we started working with 3 companies and doing research and development with those companies to work on near infrared detectors, which you do have to cool, so there's more complexity of it, but that were able to basically search for nanosecond pulses. So they would read out about at a gigahertz. And we designed and built an instrument called NIRO-SETI, which stands for Near Infrared Optical SETI. And we commissioned it in 2015 on the 1 meter telescope at Lick Observatory. So our instrument sits here at the Cassegrain focus at the bottom of this 1 meter telescope. And then we have our 1 meter telescope here at the base that feeds that instrument. And so this instrument, NIRO-SETI, would take a picture every nanosecond, okay? But it's going back to this idea about fraction of sky and sky coverage and sensitivity, would only look at one target at a time. So think back to Project Phoenix and Jill Tarter's search with Arecibo. She did a really sensitive search, but she only looked at 710 stars. In this case, in our most recent publication, we published a paper about 1,280 objects on the night sky. But this is what I call a pencil beam survey. Yes, this is great because we cover a huge wavelength and frequency space that nobody has ever searched. So it was brand new, but it's really only one pencil beam at a time. And we did this over the last 5 years using a number of students that were involved at UC San Diego. So undergraduates did all of the observing. So we trained undergraduates to use the telescope remotely and do these observations. And to highlight that, I just want to show you how much sky, if you think about this concept of duty cycle. So the movie you see here is targeting one target at a time. Excuse me. So we look at one target at a time and we observe it for only 10 minutes. Okay. All right. So now we have to think about this whole concept of time again. We have the lifetime of our universe, the lifetime of Earth, and then we're only looking at each of these targets for 10 minutes. And that gets into that other 4th parameter space, which is time. And it gets into the concept of F of now, right? You want to be able to collate that communication. Now I get a question of why did you only do 10 minutes? Why not an hour? Why not, days of each source? Well, the reason why we chose 10 minutes is because if it was longer than 10 minutes, the undergraduates got bored, so we couldn't go much longer. And if it was shorter than 10 minutes, they couldn't get much homework done and get between the observing. So it was kind of an imposed thing for our observing cycle here. But I think it's a nice movie to highlight the fact that not only do we have to think about sky coverage, we have to think about the time or the duty cycle of any of our observations on sky. Okay, so this gets us into a concept which is kind of what all of SETI wants to get to, which is this idea of an all sky, all time SETI observatory. And in 2016, our team met at NASA Ames. There was a small team of us, about 10 of us, that tried to get together and think about new ways to develop SETI to get to an all sky, all time observatory. And that developed us into something called Panoptes SETI, which I would like to spend the last few minutes talking to you about. So Panoptes SETI is a new project. And what we wanted to do to cover this, so if I go back to this movie, I'm going to show it to you. If you think about each patch of that sky I'm showing you in this movie, we need a telescope to look at that patch of the sky. So we need hundreds of telescopes. And what we tried to do in the laboratory for the last several years was to develop many telescopes at a cost-efficient way. And what we did is we developed these half meter sized telescopes, so they're about 20 inches in diameter, and to try to make them as simple and cost-effective and wide field. So what you can see is kind of the innards of one of our prototype telescopes. Now, I don't recommend ever doing this, but here's our telescope inverted sitting on the ground. And our lens that we're using for a telescope is what's called a Fresnel lens. And it has an incredibly high focus angle. So it's wide field, and you can see our baffling. And at the top part, it comes up to a focus into a detector. And all of our money and brain power goes basically into this large chip, which is able to take a picture every nanosecond, microsecond, or millisecond. And this is what our detector looks like on that back end. We have what we use are called silicon PMs, or multi-photon pixel counting devices. And they're able to read out at this gigahertz or nanosecond speed. And we have 1,024 of those back in the back focal plane here. And then we use, if there's anybody in the audience that likes this, we use ASICs and FPGAs to basically process that data incredibly fast within that nanosecond time and compare it and read out our images. And so this allows us for each one of those to take a very large patch of the night sky and take a picture at a nanosecond. Now in 2020, and I note the month, February of 2020, we installed 2 of those into kind of an old dome that they weren't using at Lake Observatory. And we put them right here. They kind of look like Samsung washing machines. And we put both of them in pairs because we wanted to look at the same patch of the sky and run coincidence between them. Now, this was great because if you note again the date, it's February of 2020, you know what comes in March of 2020. We were lucky. We installed these 2 telescopes, and then we went into what astronomers call pajama mode. And for that year, when we were stuck at home, we were working out all of our kinks and our software development for the full kind of production model of our telescopes and our observatory design. So just to see what it looks like on sky, that's what a pair of images look like. Sorry, I'm gonna take one more sip of water here. I got a little froggy in my throat. Okay, we got 2 telescopes. They look at the same patch of sky. These are bright stars. This is Procyon. And so we have a west module and east module. And what I want to highlight to you is that each field is 10 by 10 degrees. So one telescope is able to take a picture 10 by 10 degrees every nanosecond. Okay, so get rid of this targeted search. We can do a wide field search with just one telescope. Okay, and this is what an image, if we did an image of that, looks like. Okay, each pixel, I like to point that out, is 0.3 degrees. Remember that the moon is half of degrees, just to give you a scale of how large of a field this is. Okay, I'm gonna get a little nerdy with you guys today, but it's important because I wanna talk about what we did at Palomar, also all through 2021. So one of our dominating noise sources for all of optical SETI is high energy events. We call this a Trankov shower. And in astrophysics, we love to study high energy events because it tells us about very interesting high energy phenomenon in the universe. And typically on the right here, we build Trankov telescopes. Maybe you've heard of one called like Veritas, okay, which is in Arizona, or we build large areas of particle detectors. And what happens here is there's a high energy particle almost traveling near the speed of light. It hits the top of the Earth's atmosphere, and then it accelerates and dominates and hits a bunch of electrons in the upper atmosphere, and it sends what's called a shower of light. And you see the cartoon rendition of this on the left on Earth. And then the other cartoon rendition on the right is showing some event that comes in at 20 kilometers above us, high in Earth's atmosphere, hits a shower and sprays down on our detector. And we knew this about our detector, that this was kind of our noise events that we needed to mitigate. Okay, so how do we mitigate high energy events? So I want to show you what it looks like for a high energy event to come in. So I showed you some of that data for stars. Now this is a Trankov event where you have a shower of light coming down from a high energy particle that hits the top of the atmosphere. And what you're seeing is that it kind of sprays off into a cone. And this is typically what shower detections look like. Now at Lick, we installed 2 telescopes at the same site. Okay, so you can actually see when we had alignment that you had the same event in the same quadrant. And we call this parallax as parallax of 0 because we're at the same site. We knew this. And what we want to do is basically run telescopes at 2 separate sites so we can get timing differential and parallax between those events. So this is the idea of this. If you're at site A and B, you know, here in this picture, I'm at Palomar in this picture. I have A here, I would have this little lightning bolt shower strike. Here it occurs at the high atmosphere, and here in B. And what we want to do or need to do for panoramic SETI is have 2 telescopes or multiple telescopes at 2 different sites looking at the same patch of sky so we can distinguish between these upper atmosphere events. So 2 sites, I would argue in any SETI experiment actually, is always critical for unambiguous detection, but is an incredibly important for optical SETI experiments because of high energy phenomenon. Now we were interested in doing this, and so we went to Palomar several times over the last 2 years to deploy 2 of our telescopes. You can see one of the telescopes here is our washing machine. This is our early prototype unit, okay? And what you see here is a single mode fiber that we have to run and connect those 2. So here is our baseline of our observations that I'm about to show you. And then there's a site where we were camped out. So each of our telescopes has to be connected to a single mode fiber. So when we went up to Palomar, we'd have to roll this out. Here's us, I hope no one shows this to my observatory. Here I am filming something driving, but we basically had to drive and roll out a single mode fiber between the 2 sites. And that fiber is really critical because the fiber then gives us basically sub-nanosecond precision between the 2 different telescopes. And so with the Palomar data, this is what we see. So you had an event, it's the exact same event in the night sky, but you see now that it's separated in quadrants, right, between our telescopes here, and you get a parallax of 4.7 degrees. Now, what I'm not going to show you is that you also get a timing differential by thousands of nanoseconds, and you basically can distinguish in time versus parallax. And this allows us to remove all our noise sources and be able to detect things at nanosecond precision at infinity. So where are we now with the project? Oh, I have one more thing to show. This was actually pretty cool. So this is Calypso. This was an aerosol NASA satellite that's pulsing a laser down at 20 hertz. And it's pulsing a laser down to study upper atmosphere aerosols. And so we calculated right when the laser would fly overhead at our telescopes at Lick, pointed our telescopes at it. And then this is a movie of Calypso moving by. And I love this because in real time we were looking at it and we were just so excited because yes, you build an instrument to detect, pulses at nanoseconds, you test it in the lab, but to actually see it in field and work was amazing. Like, you're like, oh my gosh, it works. And in fact, we probably shouldn't have detected it. And we had to, we calculated some things and sent it back to the NASA Calypso team because it means they didn't baffle the laser as well as they should have when they were firing down. So hopefully it actually helps them with new baffling designs for future projects. Okay, so what we're trying to do now is design a new observatory where we can build many of these telescopes, put them at 2 different sites for this unambiguous detection. And this is what our production telescopes look like today. So this is our 1/2 meter size telescope. Again, it's a Fresnel lens. It comes to a focus at the back end of the telescope, which is our focal plane electronics here, highlighting those very nice MPPC detectors that read out at gigahertz. And basically each one of these telescopes then images the sky every nanosecond by 10 by 10 degrees. We're also able to we did our programming where we can take pictures at microseconds, milliseconds. And this is really interesting for that, the amazing Zwicky Transit Factory with all of these transient discoveries and multi-messenger astronomy. ideas of trying to get to other transient phenomena, maybe natural ones. Okay, so this is our current design. This is a rolling roof observatory with about 24 telescopes that we would put in them, and then you could rotate and do your field mapping across the sky. Right now we have a site selection. So we have 2 observatory sites. I can take questions on this. We were looking at Palomar, but we've recently moved at the start of this year to Lake Observatory. Our 2 sites right now are what's called the Barnard site. That's named after the astronomer named Barnard, who discovered the Barnard star, which is the highest proper motion star. And then the Crone site, which is up here. 2 of these sites, by the way, used to have houses on it. And in fact, the Barnard house that existed burnt down in that July 2020 fire, which allows this now platform for us to build an observatory. So an interesting kind of phoenix rising there from a recent fire. So what we did, this is happening, what I'm showing you in these pictures happened in the last 6 weeks. So 2 weeks ago, we had a team go up there and we installed an actual, outdoor durable fiber link cable between the 2 sites. Okay, so this is our Berkeley team unrolling a 1 kilometer fiber through the woods around, if you're familiar with Lake Observatory, all around the backside of it. And then in the last month, we installed a prototype dome at that Barnard site. And the picture I'm showing you here was taken last weekend. So we just commissioned our entire instrument and connected the 2 and are doing observations on sky. Now, if you think about how this field overlaps, okay, so this is on those 24 telescopes, you get about imaging about 1,000 square degrees every nanosecond. Okay, so in this animation, you're fixed on the sky and you let the Earth do the work to do what we call in drift scanning. You can reconfigure that and do your different types of drift scans. We can also move and do interesting astrophysical transient follow-ups with our observations. So, yeah, should I hear somebody? Here we have a movie coming in onto those 2 sites. We move in, we have our 2 observatory sites. That's the Panoptes White and Panoptes 2. We'll move down into Panoptes 1 here where we would have our observatory site. Okay, and that I'm actually following the path. We ran the fiber along that road back there all the way to the back side where you would go to our second observatory site where we'd have another duplicate observatory where you have 24 telescopes on that side. I think I see things in chats. I'm not, if somebody is moderating, I don't usually look at chat while I'm lecturing, but just let me know if I need to stop. So we'll look at the whole night sky. We'll focus on the southern portion of that hemisphere because of the galactic plane. And then you can see your field overlap within that. Now I'd like to end just with one other comment here. So this is our panoramic SETI project that we're working on now. We're in our final design phase and our prototyping, and we're even in vendor and contracting designs for quoting for building. Now, in terms of kind of big picture, I'd like to just end with a few numbers here. We have 100 billion galaxies in the observable universe. And, I always like to think about how big the universe is. We have about 100 billion stars per galaxy. And if you multiply those 2 numbers, that is a really large fraction of stars. In fact, it's just kind of unfathomably large. It's a whole lot of stars, but it's 10 to the 22 stars in our entire universe. And if we think about the fraction of planets and habitabilities and possibilities, it's quite remarkable to think about how the immensity of our universe. So there's billions upon billions upon billions of other worlds in the universe. And the interest in SETI and the interest of technosignatures is really trying to understand how in this immense universe you would do communication and even detect it. So thank you so much for inviting me here today. And I'm happy to take questions and discuss things. Thank you.
Professor Wright, that is just absolutely a remarkable set of technology. I mean, it's hard to know what to say to all that. It's absolutely amazing. We can do questions. I guess everybody should be able to turn on their microphones. Are there questions? Open the floor for questions.
I see a question in the chat, so let me just answer Jim's question. The CGX mounts can move. So we're designing the observatory where there is, we have, kind of 3 applications for panoramic SETI. One is, SETI. So that's what I lectured about today. I'm thinking about that detection. But there is also interest in trying to do multi-messenger, follow-up, like Zwicky or LIGO triggers to actually track and move there and track to look at those sources for electromagnetic counterparts. And then the third one is high energy astrophysics. So I told you those noise sources and Cherenkov showers. Well, we're collaborating with the high energy astronomers and they're very interested in our data. And we've gone to Veritas and done work with the Veritas Observatory. And so we also have a component where we log those events and we have kind of high energy astrophysics events for that.
Let me ask you a philosophical
question about the shutters in front of the focal plane. I noticed you had a couple hinged focal plane shutters.
That's for safety.
Okay.
Yeah, for 2 reasons. We were designing the observatory and we were freaked out if the actual dome enclosure never closed or something at the end of the night, or if there was lighting, we didn't want to start a forest fire. So we have a sensor there that would shutter in any bright light. It also protects the detectors. We also use it when we do darks, but it's actually mostly for safety.
Yeah, I didn't think it was for shuttering during exposure.
Yeah, that's right. Yeah.
Thank you.
Okay, let me pose my philosophical question. If you are an advanced civilization developing a beacon, now we can only do SETI with the technology we have, but if you're a very advanced civilization, you get to choose the technology of your beacon. So therefore you get to choose what kind of civilization would be able to receive the beacon or understand it. And if you're very advanced, maybe you have the ability to attack another planet. Now, if that's the case, they would not want to send a beacon at their technology level because there might be a reciprocal situation. But if they send a beacon at our level of technology, they're safe. Does that, how do considerations like that affect, the whole scheme? Of course, we can only use our own technology, so we're limited. We don't get this choice. But do you think the beacon makers have a choice like that?
Yes, they do have a choice like that, and we have it as well. And I love, your philosophical questions. I'll make them plural because there's a lot packed into it. So the first point of it is it's kind of touching upon Fermi's paradox, actually. So you can think about Fermi's paradox as saying, okay, if civilizations last for millions of years, why haven't they populated the galaxy? Why aren't they visiting us? And there's many people have solutions to this, and one of them is almost to your question's point, which is if they're millions of years ago, maybe they're using a technology for which we can't detect, and they're only going to talk to more advanced civilizations, right? So there's already a galactic network out here, and we're just not part of the club. The other component of your question has to do, I think, more with messaging. And Carl Sagan has some really great quotes about, you don't just walk into an unknown jungle and start announcing your presence and screaming your name, I'm here, right? And so, that gets into a lot of ethical questions about communication. Everything I've talked to you about today is very passive, right? We're just trying to understand the jungle and see what may be communicating and using the means for which we can best use them today. But there are people that, we do leak our signal, and there's a lot of questions about messaging. So, we have sent beacons. We have done that. We did that in the 70s with Arecibo, and we have some few kind of rich individuals with means that have used major telescopes to do signals in the last decade. And so I think there's a lot of ethical questions we need to think of as a society and as humanity as a whole, because I think we'll continue to see people that can just send beacons.
Wow.
So maybe we're looking for rogue civilizations like our own then. I don't know.
This is Javier. I have a quick question. Given the equations that were presented, right, in the billions, and then billion on top of billion, why have we not received, or why have we not, or maybe we have and it hasn't been disclosed? Why does society not know factually about these beacons?
I think it goes to my other part, Javier, that's a great, it goes to my other part of the talk, which is we really haven't searched. So, we can put interest, I think in this next decade, we're beginning to put means into the SETI community that we can start placing limits that say, you know what, if there is a civilization, they're not using this communication or this frequency at this sensitivity, right? So I think we can begin to do that. And then the answer to your other portion is, maybe they're not nearby. Maybe civilizations are rare. Maybe there's a great filter ahead of us, things like this. But it doesn't predispose like other life, other intelligent life, or even other civilizations that we haven't detected yet.
I have a question. Can you hear me?
Yeah, I can hear you and
I
see you,
didn't know if I
Tom.
had-
I can hear and see you.
Okay, thank you. I'm also a fellow at the Arthur C. Clarke Foundation for the Imagination at UCSD. And this has been a hot topic for years. And David Brin has been holding a group called METI, Messaging to Extraterrestrials. But the specific question I'm been pondering for quite a while is the notion of pruning out the search tree to the locations that are most interesting and most fruitful. And if they are putting out a nanosecond pulse every year, what's the chance of seeing that nanosecond? So my question is, finding stars or planets or civilization or planets that we see their transit and they can see our transit and they could see our oxygen, we could see their oxygen. So now we have this paired protocol that they're coming around the sun and we would see that transit point. And that could be a synchronous clock that would say, okay, here we see you, they're there, we're going to pulse you at the exact time that's most critical. And then we would be able to talk back and forth. Is that a situation that you've looked at? And does it make sense as a way of pruning the search tree?
Yeah, it's a great topic. So thank you for bringing it up. When we do targeted searches, a lot in radio and in optical, we do it's called an ETZ. It's called an Earth Transit Zone. And it's the lovely idea that you stated, which is the solar system lives in a plane and maybe there's another system that lives in a different plane, right? But if they are aligned, then you could think about communication. It also tells us something about in Kepler, when we look at transiting exoplanets, when the planet moves in front of it, we can measure its atmosphere. And then this gets into this premise for which you were talking about, like by understanding its atmosphere and biosignatures. So we have a target list that's shared among all SETI, it's public, and we reverse calculate it. One is their transit zone to us, and then what we call ETZ, Earth Transit Zone. So if they were observing Earth, what stars would be co-aligned with our solar system? And there's a beautiful target list, and we put that. So even the NeuroSETI targets we had, about a couple hundred of them were called ETZs, which were their systems looking at us. And in our paper, we go into that discussion of, if you're going to look at some stars, which stars do you look at? For something, we love thinking about this, and it's a great topic. For something like panoramic SETI, right? It's kind of just pushing that all aside and saying, you know what, planets are everywhere and the sky is big. Let's just look everywhere, right? And don't get constrained about if, that, what, right?
Yeah.
Which gets into this large idea of large fractions of the sky, which, I like thinking about these transit methods, but I almost think it's kind of constraining. So you should probably just try to look as much as possible. I also try in the searches, we do what you do, but with our team, with undergrads and stuff, I said, you know what, let's throw everything out, all those papers out the window, and let's look at oddball sources, right? Like stars that look funky or have odd colors, or let's make a list of things that just don't look quite right in our catalogs. And look at those.
Well, coming from my information systems background, I would say what discovery would have the greatest meaning, most meaningful discovery search algorithm. So seeing someone who sees your transit, ETZ, is that what you call it?
It's called, I'm happy to send the paper, it's called an ETZ, yeah.
Okay, ETZ. Trims that, number one, and it also gives you a focus point to go at. And then to relate this to the amateur astronomy community that could put up an 8-inch scope all night, once a week or whatever. So it could have an intense temporal viewing at less resolution, obviously. But would there be a place for amateurs to join in and do a SETI at home type thing with their scopes?
Yes. The answer is for optical study like this, you don't need a large telescope. And I think anything that is measuring brightness versus time on objects is incredibly interesting. And if you were to do a targeted search on, things like Earth transit zones or other transit zones. The other thing I want to say to point out for your nice comment, Tom, is that in SETI, the parameter space is so large. So carving out a space where you can say, I searched this and nothing was there is a nice way to define parameters.
Yep.
But I think looking for transits, you're doing too much pruning. That's just, you're cutting yourself down to just a teeny weeny fraction of all the possibilities there. It strikes me, it might be something that amateurs could do, but it's just such a small number of possible stars. Doesn't strike me as a fruitful way of doing it. It might be fun, but it doesn't strike me that it's likely to have a discovery there.
Depends on how common life is.
Okay.
Yeah.
So then you're in the probability function, but yes.
I don't want to hog the discussion, but I am. What about quantum computing and quantum weirdness type stuff going on and communicating at something other than optical levels of communication? Is that even in your worldview at all, or is that science fiction?
Not, I don't know how to answer that. It's not, there's some very interesting studies on quantum entanglement and, kind of quantum detection at the detection limit of detectors. So the detectors we work with are kind of pushing the limits there. So if you put it on a very, very extremely large telescope, there may be interesting areas of study. So in essence, our technology moves into that area, and we work with some people that work on very fast response detectors that are sensitive kind of to the single photon detection levels. It's not my area of expertise. I don't think this is just, I think we're being recorded, but I don't think we're there yet. I think we have some ways to go.
I'd like to follow up offline with some of these other things if you don't mind, but
Sure.
thank you.
Other questions? Other questions? Can I?
So right, this is Mark Baker, but
Yeah, Mark, go
I
ahead.
would find that the time is such an obstacle, because like you say, we could be looking at some place and they could be a civilization just like we are at this time now. But if they're 10,000 light years away, yeah, they're existing now, but we're never going to probably see that signal, and vice versa. So, I'm really excited about what you're doing, but the aspect of time would really bother me.
When I teach on astrobiology, that's one of my biggest themes is about time, right? That really is the greatest factor here in terms of longevity to life and civilizations and detection, and coexistence. And sure, like if you have a civilization living, 1 million years or more, you don't care about 10,000 years, right? So, or 1,000 years, or 100, 200 years. So that long pen pal discussion over cosmic distances doesn't matter as much, right? It's kind of similar to thinking about the length of a lifetime of a species and how that species interacts with their environment. It's very similar. But yeah, we have to contend with that, right? Even in 100 light years away, it's 100 years ago.
Basically, we have to wish everybody out there well, so that we can eventually make a connection, so that we don't come and go and pass each other like ships in the night. So
Yeah, I mean, if we ever make a detection, why does it, I think it's going to mean a lot to
No,
humanity.
Professor
Oh.
Wright, no, it's not when, it's not if, it's when you make an action. So
We hope.
So we have 38 people on this call. Raise your hand like this if you think there's going to be a detection within our lifetimes or within the next 100 years even. Raise your hand if you think there's going to, look at that, 1, 2, 3, 4,
What
5,
type of detection?
I'm doing
Ah.
research.
any kind of detection.
I think we're going to discover life on another planet very soon.
Oh, that's interesting.
Yeah, I think that can happen in our lifetime. I think we're going to find biosignatures.
Let me ask if this is a factor. If you're building a beacon, it's not necessarily going to be isotropic unless you can modulate neutrinos and do blast and things like that. So more than likely, there's going to be a narrowband or a focused beacon. So the beacon maker has to have a choice of which possible areas does he want to illuminate, and therefore force a detection. And if these guys are that much more advanced than we are, maybe they've detected us, so they have a choice. Point your beacon at these Earthlings.
That's correct. If we were to send a laser to another signal, like a system, the dispersion of the laser disperses, so you can encompass that beam across the entire solar system. But you do also, because of the distance of it, have to calculate the proper motion of that star and lead that signal. And that's similar to even radio broadcasting too. And so in terms of beaconing, there's really nice papers, several papers, even about how you would take present day technology, even communicating with lasers, and say, I could put a laser in space right now, get several mirrors and broadcast to tens of thousands of stars very quickly. So I could say, I know I've already done my sim missions, I've done James Webb, I'm already 100 years ahead. I know where all the planets that have life on it within 10,000, and I could beacon them all.
Yes.
But the ethics of that is one person or the most extroverted party would be the one to be talking, and the ones that don't want to open the kimono are exposed regardless. So there's a reason for constraint, but politically and socially, I think the most outrageous person will be the one to lead on that issue.
Tom, that probably is true for humans. I'm not sure. It's hard to predict for another species, but yes, it seems like you're right.
I was going to ask about other species, by the way. I mean, I'm into blue-green algae right now, 2.5 billion years, and it's still messing up our lakes here. If you look at them, and there's some weird communication going on in an algae bloom, and animal to animal and plant to plant communication that I think we're discovering. Could it be that nature is communicating at, say, a blue-green algae scale, where the baud rate might be 10 to the minus 10th hertz, and just very, very low bandwidth, that they've somehow figured out how to propagate their information out of genetic communications? These gamma ray bursts could be their communication tool.
Yeah, there was a recent paper, I think, in Nature about how fungi communicate, right? And it's incredibly complex, as you say, and they can do over long distances between their kind of their cells within it. And I do like to think about that, not just in the high energy astrophysics, but in low energy as well. And then, of course, there's nice people thinking about, well, what if there is something on gravitational waves? I mean, that's a very weak signal, but we have animals that are able to navigate with our magnetic field to Earth. So it's interesting to think about how species interact with their environment and that evolutionary trait of how to navigate it. I see a hand. Sorry, I just want to make sure Richard has a hand too.
Yeah, thank you. Yeah, I'm an amateur and a hobbyist. I'm a bit in awe of all of the scientists here. But can you tell us, or me, why you think that we'll get a yes signal or an affirmative sometime in our lifetimes? I'd be fascinated to know that.
I raised my hand that I think in my lifetime, or our lifetimes here, that we'll detect life. I think life on another surface. I'm not sure if we'll get communication. I don't do I'm just struck by this, having done this for my career, I'm struck how little humanity does this given its resources. Like, we really haven't searched that well. And, we can sit here and have many beers and talk about all of these and wax poetic about it, but we really just don't know, and we should be out there searching. And so I don't know the answer to the communication aspect of it, but I'd like to know that answer. And I think if we do these searches, like the searches like Panoramic SETI and other team searches, I think we can apply important constraints. A null result becomes interesting for all of these reasons we've been discussing. So I tell students this too, like, I don't do this search because I'm expecting to get a signal. I do this search because we should be doing the search and we should be able to provide constraints on it. So to answer your question, I don't know. I think the lifetime of a human is very short in the lifetime of the universe. So it's a hard sliver of a piece of paper to say if I'm going to co-align with such a historical event. But I do think we're putting up the technology now to answer if there's other life, like, bacterial life on other surfaces.
Melvin had a question. Melvin Sanchez.
Yes. One thing about the ethics, I think it seems to me that those questions are actually more about our self-interest, because ethical questions are more about harm and, are we causing harm to anyone by interacting with them, or are they harming us? But my quality, I like what you said about that you're very positive, that we will find something. I don't know the math well enough to understand the Drake equation. So I was wondering if you could just give me like a very lay person's explanation of the probability of it. So in terms of your optimism, is it based on a probability? Because for me, it seems like a matter of probability, like, very low probability or very high probability. So since I don't understand the Drake equation, I was just wondering if you could maybe just give me a layperson's explanation of how good the probability is, right?
My answer to this is that the probability just gets better and better the more we learn. So the Drake equation, when Frank Drake was writing it down, was trying to understand the probability of other civilizations coexisting with us, right, in the Milky Way. And in 1960, they didn't know other things, like they didn't know how common other planets around other stars were. In fact, they thought it was not going to be common. They didn't know how common Earth-sized planets would be. They did not understand fully a little bit more about the evolution of stars and how stable stars and orbits of planets were. So in that course, in the last 60 years, you take every factor in the Drake equation and it's trying to get to that number of stars, fractions of planets. And everything we keep learning about astronomy, biology, chemistry, geology, all of the things we've learned have pointed towards, more and more habitable surfaces every decade. So I would say the odds of this keeps improving. So, but in those factors I showed you, Melvin, there are things we don't know. Like we don't understand, like evolution is very complex. We look at the origins of life, these things that we're trying to study today. So if you take Drake's equation, what I love about it is you can see all the sciences embedded into each factor. So that if you could take all the people around the world doing research, they're kind of trying to research each factor of the Drake equation. So I don't know the probability, but I hope what you take out of the probability of the Drake equation is that it really matters how long a civilization lives for. And from what I can see of our civilization, we are probably our greatest filter.
Thank you. That's very helpful. Thank you.
Professor Wright, can I ask, kind of something I missed somewhere at the beginning. What in Panoptes SETI, what do you imagine, what do you foresee, what constitutes a positive signal
In any SETI experiment, we set up a method for, detecting candidates essentially. So a positive signal would be a signal that's detected. It's essentially at the distances of the stars. It's between the two of them, and it has the exact same timing precision of it. Now, if you get one of those signals and it's bright, that could be what in SETI we call a wow signal, because it never happens again. So what we hope for is that it repeats.
Okay, yep.
So you have a secondary detection, or the signal's continuous, for which there's follow-up strategies, which we have as well. So if we get a detection with Panoptes SETI, you say, oof, we got a detection, what exact frequency is that? We'd be following up with multiple telescopes. Then the fun part becomes, right? Because then if you guys have seen read Carl Sagan's book, Contact, or watched the movie Contact, right? You get a signal, then what? Then you're gonna spend all your time decoding that signal. That's almost harder than the detection part.
Okay. Yeah, that's a challenge. We're getting along in time here. Can I ask, are there other questions? One more question, Charles? Well, then can I close with, why are we so fascinated? Why is this such an important topic? What's the draw? What's the attraction? Why do we want to know? Why do we want to contact?
Is that a question or a statement? But if it's a good question for me.
Well, it's a little both, I suppose. Have you considered what it is? What's the driver? Why?
I've never met a human on planet Earth that has not been interested in this question.
Yeah.
And it's simply about existence and understanding our place in the universe. And when I end every class I teach at UC San Diego, I end with the phrase, be curious. Like I always wish my students, when they go off in their life, whatever they do not lose the drive of curiosity, because it's one of the most powerful emotions that humans have, right? So in essence, it's almost our curiosity to the core, like this fundamental question of why we exist and our place in the universe.
Well,
I
thank you.
think in the history of science, we've come across this question before. When Copernicus showed us that we're not so special, and Galileo showed us that we're not so special. It seems to me that it's the same theme again, right? It's the same thing repeating itself in science, which is great.
Well, we've been at this for almost an hour and a half. Professor Wright, you've been very generous with your time, and we thank you very much. Fascinating presentation and good questions.
Great discussion.
Great discussion. So I think bring the meeting to a close. Let me simply mention that next time, well, you see, next time it's hard to get anyone to speak on July 4th weekend. So we're gonna skip 3 weeks, go to July 9th, and docent Mike Burton. Mike, you're on in 3 weeks with a presentation about, title is Galileo's Finger, right?
Yes.
And
Mike knows him personally, so that should be a great talk.
oh boy,
It is a great talk.
it is a great talk, and we're going to get into trouble with this. That's
Looking forward to
July-
that.
That's July 9th. So with that, thank you again to Professor Shelley Wright. My thanks to everyone. Thank you all for being here and attending the Greenway Talks online. And with that, I'll close the meeting And we'll see you on July 9th. Everybody wave.
Wonderful talk.
Wonderful talk. Thank you very much.
Thank you.
Thank you.